If you haven't gotten your meal card, come get it right now, real quick. Need it for lunch. Okay? Everyone have their meal card? Come get it now, real quick.
Gosh, making me nervous.
You need the.
We are running slightly beyond the schedule, but that's why we're here. So, and beyond the schedule every day, I believe. The more the merrier. So the lecture before lunch today is the proper introduction of QCD and electrons. George Sterman.
Thank you. And thanks to everyone for coming all this way, however long it was, to Stony Brook. Let me ask, how many of you would describe yourselves, and you can answer yes to both questions, as experimentalists and theorists? So, well, probably there's a slight leaning towards theory. I'm going to start with, I guess would be standard apologies. Even more than Alexei, I'll probably be waving my hands at to the point where you can't even see them. And what I would really like to encourage everyone is to ask questions. The basic question is, why that? I'll say some things and you'll have heard them before. Everything, especially the theorists, I imagine, will have heard almost everything that I have to say once before. But it can be an opening to a discussion, maybe a different way of looking at it than the way in which, the context in which you heard it the first time. So I really, really want to encourage people to ask questions. I have another reason for asking people to ask questions, and that is, this is slide 1. There are only 66 slides, and I have 3 lectures. So give me a break here, slow me up. Okay. And of course, should I get through all of them, well, you know, I'll come up with something else for Wednesdays. So these are the introductory talks, and I should also apologize for not being here as I originally planned at 9 o'clock, but I just, for other reasons, wasn't able to be in this room at 9 o'clock. But here we are, and I will be here, as they say, God willing, tomorrow at 9 and Wednesday. So this is an introduction to QCD, and with particularly and electrons, and why electrons are special in this context. So this for this school, and I will say openly, these are almost identical to the lectures from that I gave a year ago at this school, but I assume there are no repeat offenders. I mean, like, nobody failed the school as far as I know, where they had to take it again. All righty, so here's an outline. starting with light and photons, the hidden universe. So this is all very qualitative, but at the same time, I think it sets the stage for what we're trying to accomplish in constructing the EIC and doing the experiments that lead up to the experiments at the EIC. And both historically and those, many of which you're already involved in, at Jefferson Lab now, for example, or in Europe. Okay, good. Now I have this thing in which I will. Aha, okay, so we're going back, all right? And light and photons, this is the first. There's 6 little items like this. And if we get through 2 of them today, we'll be right on schedule. So here it was, 1905. The wave theory of light, which operates with continuous functions, has proved itself splendidly, said Einstein in 1905. But continuing with the quote, he said later in this same famous paper, one should keep in mind, however, that optical observations apply to time averages only. The energy of light is localized at points, right, in space and can be absorbed or generated only as a whole. So where is it? Okay, I would just like to hear another voice. Where is it that is localized? It's localized at, what do we call it? Come on, you know this answer. I mean, we have electrons and we have, all right, we have positrons. No, I want to hear another voice. I'm not going forward. The photons, every single one of you knew this answer. I say it with complete confidence. And, well, okay, and if you didn't, it's just that I was being so confusing. Now, it's interesting to notice, actually, that it's the very, historically speaking, the very same person who actually really proved that the wave theory of electromagnetism was, in fact, the wave theory of light, was Heinrich Hertz. He was also, as it turns out, the discoverer of the photoelectric effect, where he saw that there were subsidiary sparks, and this is a picture of a translation of that result from 1887. Okay, so that was about, well, it's 15 years before the famous Einstein's positing of what we now call photons. He didn't call them photons. It's just quanta of electromagnetism. So in any case, the density of photons is proportional to the square of the wave amplitude, and that's where we start. And in some sense, this is the beginning of everything that's in this workshop, this school, and in the language of all of the experiments carried out at accelerators. It begins really with this observation, that it's at points that waves are generated. So this sets, as I said, the stage for many great discoveries of the 20th century and into the 21st century, where you may recognize this as, here we have, well, here it is in pictures. 2 protons collide. Gluons are present in their virtual states when they come at a very, very small impact parameter, to use the same term that Alexei was using. And when the gluons come close enough together, they can interact through a top loop, producing a Higgs, and the Higgs can decay to a ZZ star. So a Z and an off-shell Z, because 2 on-shell Zs are too heavy for the Higgs, but it is a particularly clean, although somewhat rare, K mode of the Higgs, producing 2 pairs of electrons and positrons. And you add them all up and it adds up to 125 TeV. So here they are. Here's our electrons here, and the pair here and the pair here. So this is the language, and the language begins with the observation, the explanation of the photoelectric effect, that there are point-like particles at the essence of matter and forces. So here's something that we've all heard, of course. Emergent degrees of freedom are a universal feature of classical and quantum laws of nature. At scales, we can see from hydrogen gas to galaxies and stars. There's a huge, huge gap in the scales, but through gravity, structures form. From atomic magnetic moments to antiferromagnetism or ferromagnetism. From molecules to phases of matter, snowflakes and all that kind of stuff. From electrons and metals to superconductors, and from chemistry to life itself. This is a Rousseau painting for those in the back. Oh, by the way, am I speaking loud enough for people at the back to hear?
Yes.
Should I stop speaking anyway? Okay, hold that thought. All right, and at the micro scales, now we're getting into the subjects that we're talking about, from protons and neutrons to nuclei. We've known that since, since the discovery of the neutron, which was around 1930 or 32. And from quarks to protons, neutrons, and other baryons. And so that's, of course, the great discoveries of the 1970s, in particular through electron scattering along the lines that we'll talk about. At each step, the compound system has features qualitatively different than those of its constituents, yet following from the properties of those constituents. Okay. And to some extent, to a large extent, each of these steps and each of the examples I gave they're understood at different levels. But it's the further understanding of how we get from these quarks and gluons to protons, neutrons, and then eventually to nuclei. That's the subject of the research we're talking about now. Okay. So currently, and now in some sense, this, again, going back to the photoelectric effect explanation in terms of what we now call photons, this is what it all led to. Over from 1905 till, say, the discovery of the Higgs in 2012. So a period roughly of 107 years to accomplish this. Everything we can see, which is to say not dark matter, is made up of matter and forces and force particles that are players in what I'd like to think of just for this lecture as the game of the standard model of elementary particles. And I'll try to show you why it's useful in some ways to think of it as a kind of a game. We have, of course, baryons or three quarks. Here are the quarks here in this, let's see, I guess I have this nice light here. I don't know if it works. Okay, so the quarks are in this square, in this rectangle here, three up type and three down type, specified, distinguished by their couplings to the weak interactions, and the three charged leptons and the three flavors of neutrino. So the gluon, the photon, and the Higgs, and here we have the Z boson, the W boson. So here's the scalar bosons, and here are the vectors, the massless vectors, gluon and photon, and then the Z and W massive vector bosons. So, yeah, I mean, here just noting spin 1/2. Whoops, okay, here's my first problem here. Oh, I did two. Okay, here we go. All right, of course, fermions, which are the quarks and the leptons, are kind of the matter. They're spin 1/2. The basic quantum of angular momentum and force. So force particles have spin 1, except the Higgs, which in some sense is a force particle, but is primarily a matter giving the mass. The spin directions can change, but the spin never, ever slows down. So spin 1/2 now has been spin 1/2 since the beginning of the universe, as far as we know. And it's as if the electron were spinning or the quarks are spinning, but they never slow down. There's no friction there. involved in that. And that's something which shows what a great discovery it was, because it had to, the realization that you have angular momentum degrees of freedom associated with these point-like particles, which were begun with a photon, is an extraordinary jump from a classical point of view. How can you have motion that simply encounters no resistance? All right. But in any case, here we have our friends, the up quark, the down quark, and the electron. These are the ones we make. Most of the visible world is just out of these three particles, mediated by these three, and then the Higgs giving a little bit of mass to the up and down, or at least so we think. The neutrinos we don't normally see, but they're all over the place. The electron and the muon neutrinos because of neutrino oscillations. Okay, so here are the forces with the same diagram in the upper left. Our friend the gluon in red here binds together these all the kinds of quarks into hadrons, most of them unstable, but the up and down hadrons, proton and neutron, are the lowest lying ones, are stable, essentially completely stable. Well, at least the proton is completely stable. The neutron does decay to proton and leptons. And then for the photon, everything that's charged, so all of the quarks and the charged leptons. And finally, the weak force, the W, the Z, and the Higgs involves all of the matter. And the Higgs doesn't couple directly, whoops, it is, to the photon, but indirectly through the top loops that we saw before. Okay, so you might say, okay, whoops, let me just make sure that I'm doing the right thing. All righty, so where have they been? So we see indirectly, we see the up and down quarks, but it took the slack accelerator to see that through deep inelastic scattering, which we'll talk about a lot. But aside from that, the only thing that's really readily visible was the photon and the electron through the photoelectric effect. So where have all these particles been? You get, I mean, those two, the photon electric and the electron, are on that table, but they're one of all the others, which are about 15 of them or so. So why didn't we know about the Standard Model before the latter part of the 20th century? Well, right after the Big Bang, so we'll think common cosmology knowledge, things were really hot, they were moving fast, the universe was expanding fast, still expanding fast, but it's much bigger now, so we don't notice as much. So right after the Big Bang, all the particles mixed freely. Decays were balanced by production. But as the universe expanded and cooled, the high energy collisions, which are just associated with the temperature of the particles at that time, began to cease. Heavy particles are decayed and not replaced because the replacement would require high energy collisions, which would require high temperature that was dissipating. And now, however, it's not, however, from this point of view and from the quantum mechanics point of view, these high energy particles have not disappeared, but rather they exist in virtual states. They're all over the place, but they exist only for very, very short amounts of time. And we'll go over why we say that from the point of view of quantum mechanics as we go along in this very, very introductory lecture. So in addition to that, so here, that's what, let me get this thing here. Here we go. Heavy particles decayed and were not replaced and are now found in short-lived virtual states from which they can emerge only when sufficient energy is supplied to them. And in this observation is the motivation for accelerators. Okay, we find situations where we can bring those virtual states to life. So yet other components of the universe appear to be hidden from us by not sharing electricity and magnetism, and perhaps also not the weak interactions, and that goes by the name of dark matter. For some reason, it skips ahead too. So At the meantime, so this is what happened to the heavy particles, but the stable quarks and gluons retreated to the tiny volumes of protons and neutrons, surrounded at great relative distances by electrons and protons in the form of atoms that form molecules that form us. Okay, but the idea here is that they are in this tiny, very tiny percentage of all of space-time or space at any given time that we see, all of the quarks and gluons have retreated into this volume. But I mean, in some sense, that's an overstatement because they exist as well, flickering as photons propagate. In virtual states of photons will produce pairs of quarks in addition to electrons and positron pairs that can be excited in the same manner. All right. So experiments in theory and electron-hadron colliders seek out matter in each of these realms. Realms of the very heavy to produce heavy states that are generally to realization of virtual states, and to break up the confinement, as we are used to calling it, of the quarks and gluons in the hadrons. So we use the players, the quarks, gluons, electrons, and photons. And quantum field theory provides the rules of the game. So we'll talk a little bit about quantum field theory in this first lecture. At Jefferson Lab, for example, what we're doing, again, oh yes, here it is. Electrons here are accelerated around the loops, and the nucleons wait for them in the experimental halls. I mean, I often like to anthropomorphize particles. You know, after a while, you think of them as your friends. I hope they think of us the same way. How do those protons and neutrons feel? Oh no, not here again. Well, you know, it's like that. I mean, think about it. These quarks and the quarks that make up a proton, how long have they been together? And a proton that we find, you know, let's dig up some dirt and stick it in there, get out some element or other. They've been together in some meaning of the words they, been, and together. Okay, but in a way that in this approach you can think of since the Big Bang, since nucleosynthesis at T equals whatever it was, 2 minutes or something like that, after the Big Bang, whatever the Big Bang was. All that time, you put them in Jefferson Lab and send electrons in, and it's like, well, it's been great knowing you. I'm off to a meson, and heaven knows what will happen to me there, but I don't feel good about it. And the other one says, oh, I'm off to a proton. Well, I'll have new friends, and maybe we'll be lucky enough not to go to another accelerator. All right, well, anyway. So, right. So quantum field theory in these situations tells us what's going to happen, and it systematizes the duality between fundamental and emergence. We use each to explore the other. We use these elementary electrons to probe the emergent protons made out of quarks and gluons in this particular case. But also it works the other way. We learn about electrons as well. Oh, no, I went back. Here we go. So higher energies will require colliding beams and EIC. And so here it is, at least as it appears on the Brookhaven website. I notice the polarized electron source. The idea is to use that polarization component that we had at RIC and now will be incorporated into the EIC to really understand the dynamics of the spin, as well as the way momenta are shared, both longitudinal and transverse. I know you heard about already, and to try to really test the three-dimensional structure of these emergent degrees of freedom that we know as the proton and the neutron. So now, so that's the introduction. So completely non-technical. Now we're going to get a little more technical, but just the sort of the rules of the game. And why, to some extent, it seems to me it's useful to think of quantum field theory, to think of QCD or discussions and the kind of experiments that we do as using a certain game that's built into the structure of the universe. So the rules, well, the rules, if we had to give it a name, we could call it the Schrodinger equation. This is just everything is the Schrodinger equation. I mean, we discovered the standard model. We postulate string theory for that matter. The Schrodinger equation is still true because we are using as our paradigm quantum mechanics. And so after a little bit of work and, a semester or so of quantum field theory, we come up with the following rule or a set of rules. And the set of rules exactly incorporates the Lagrangian of the quantum field theory that we're working with. So what we end up, for delta t, a small time, okay? We start out with a list of particles. It should have said this. But then that list of particles changes, okay? So this is our picture of the universe. Our picture of the universe says there's a whole bunch of particles, and then given our quantum mechanical information, we know some are moving up to some uncertainties in certain directions, and they're located up to some uncertainties, so that delta x, delta p is greater than or equal to h bar. That's it. That's the whole universe, okay, at a given time. But what makes the universe go in this picture is that that list of particles will change. And we do it in quantum mechanics, so we assume that we have an amplitude, and the amplitude for the new list of particles at t plus delta t is equal to delta t times a rule for changing the list times the list of particles at time t, okay? And so again, the list of particles at time t is an amplitude, so it doesn't specify exactly that. It says, oh, whoa, we have I don't know anything else, but I know this is a proton. I saw it, okay? I trapped it here in a magneto-optical trap or something like that. No, it's got a little electron, but whatever. Okay, so it's a proton. So I know there's some list of particles inside, but I know this is quantum mechanics. So I know that list keeps changing all the time. It's flickering, and it doesn't take on any particular information aside from what our conservation laws tell us, like baryon number 1, charge 1, spin half. But I can tell things about it. I can tell how that list, whatever it's composed of, will change in time. And the way I do that is through quantum field theory, the rules associated with it. So we represent, so here's just the observation. This is really just the Schrodinger equation. This sort of d by dt of the amplitude is the Hamiltonian acting on the amplitude in the interaction picture. And the rule for changing the list are the interaction Hamiltonians, or the vertices of the theory. Okay, so we represent these lists as a quark or a lepton is an arrow, anti-quark or anti-lepton, the arrow in the other direction. Of course, I didn't tell you which direction's which, but it becomes clear from the context. Photon or a weak boson's a wavy line, a curly line's a gluon. Okay, so that's the list of particles in a possible configuration of the fields associated with those particles. So why is it only that? Because that's what we found in the standard model over the last 100 years. This is all we found. Now, of course, you say, isn't there dark matter? And many, many models will have dark matter. So there'll be other lines. Maybe I need new symbols, little like symbols like cards or something like that. I don't know. Anyway, that's what we have in the standard model. So these are what I will, after all, I'm giving this lecture, so I have to use words like beautiful, because the beautiful theories of the standard model, and I should have, I think I'll put it in at some point, the Lagrangian for QCD, but I'm certain everybody here has seen it. And what the Lagrangian has are some kinetic terms for gluons, for quarks, Ws, photons, that really have a one-to-one correspondence with the kinetic energy of particles, just like the particles we've described, moving. And at the same time, it also has some interaction terms, and the interaction terms give the vertices, and we can think of the vertices as the rules for changing the list of particles. That's what we're doing. We're imagining, what we do, of course, is we do experiments where we change the list. If we see how the list changes in some tiny little portion of space-time, where we have a collision, either in a collider or a fixed target experiment. But in fact, our picture of the universe from this point of view is the whole world is doing this all the time. Now, you can judge for yourself whether that's a bit of a jump. Are we, pushing it by saying things like that? And that gets you into ideas about what's the role of science, what does science have to offer to the world? Well, okay, these are all good. But in any case, here we go. We have rules that involve three particles. Okay, so that's these, the 3-point vertices, one which has associated with a charge E, and that tells you something about, it tells you about the rate at which this will happen. The delta T is equal to this rule times the amplitude. So this rule says as E, if we were to change the value of E to be greater, this would happen more often. It would happen faster as the time went on. If we decreased it, it would happen slower. The charge, the strong charge, GS, where a quark and an antiquark coupled to a gluon, 3-gluon coupling, and then a 3 weak boson coupling, say between W's and Z's, or W plus and W minus and Z. And then we have 4-particle couplings only involving, in the standard model, the vector bosons. Well, now I should say, these are the Yang-Mills theories version here. There is a 4 Higgs coupling now in the standard model, which I didn't observe here. And actually, if the EIC wants to understand the proton structure, which we really, really know is there, the Large Hadron Collider over the next 5 years is desperately hoping to get the 3- and 4-point couplings involving the Higgs, and hoping at least to put limits on it. And it's very, very difficult because those are very weak interactions. The particles are heavy. Virtual states live for very, very short periods of time. There are huge amounts of backgrounds. Yeah, I mean, QCD is easy this way. Well, anyways. Okay, but this is the QCD part here and QED. So notice that, and this is the putting quantum theory together with relativity to get quantum field theory in the standard model. All the time directions in this picture are allowed. So, for example, if we imagine time as being here in, what direction is time going? Well, it could be anything. Here, if time goes up, okay, it's kind of like time is going horizontally here. So we could imagine an electron comes along and absorbs a photon. So we had an original list with an electron and a photon. Now there's only an electron. Now by itself, it wouldn't be on shell, but hey, that's it. This is just the next flickering moment, so it doesn't have to last. Or a quark could come along, absorb a gluon. 2 gluons could come and fuse into a gluon, and so forth. So now 2 vector bosons can couple to themselves. So if these have time going this way, you can rotate these and still have time going this way. And so you have 1 particle going to 2 instead of 2 to 1 in all the possible ways. And like this, you could have pair production. And at the same time, you rotate them again, you can have a pair annihilation into a photon, an electron positron, or a quark pair to a gluon, or two vector bosons to another vector boson. So all of these are possible, and that's a consequence of relativity, as was observed in the basic case of quantum electrodynamics by Dirac at the end of the 1920s. So here's how it works. I don't know. Well, I couldn't think of another question to ask you. So I guess everybody's seen this in some sense, but is there, somebody like to say anything? Or any idea thrown out here, how it connects to another idea that you heard about? Well, what about? So think about, yes.
So in that new particle list, can we have some bound states?
So the question here was, in the new particle list, can we have bound states? And as it stands, not yet. Okay, because we're working only to one order in perturbation theory, which is the size of those couplings. So here, we're doing this over those times, and we're assuming there is a time short enough so that picture in terms of a list followed by a new list, which differs only by those vertices. The action of those vertices is a good picture. Now, how do bound states form? Well, the simplest, we imagine we keep doing this many, many times, and a set of particles that keep interacting with each other change the amplitude in such a way as to produce a pole. There'll be a pole in their relative momentum, and then a bound state can appear, even in a very, very simple theory. That's actually what I wrote. I wrote a thesis too, actually. Kind of pre-QCD, but well, as far as I knew, it was pre-QCD. It wasn't really pre-QCD, but it was exactly seeing how that works in a simple theory. In that particular case I studied was the Yukawa theory. So what happens is you have a pair, could be quark and antiquark, but it's just two fermions, and they keep emitting a scalar particle, and then one emits it, the other absorbs it, and it goes back, right? And so that process, of course, goes in both directions. First one emits it, second one absorbs it, the second one emits it, the first one absorbs it. And then when you add up those processes, each with the exchange, it's a set of so-called ladder diagrams, and you find that there is a pole in the invariant mass and the amplitude when the invariant mass of those two reach some scale, and the scale there is determined by the masses involved and the coupling. And that's how bound states would form here. So we see immediately, this is like a perfect question, because it shows what you can get by treating things this way is what you get at fixed order in perturbation. You won't see in this picture yet the formation of the bound states. And of course, are the bound states interesting? Well, why are we building the EIC, right? I mean, yeah, they're really interesting. Okay. So thank you for that question. It lifts my spirits. Okay, so here's something which I think it's an idea that I share with you. And every time I even read it, I feel it's saying something and I don't know what it's saying. But anyhow, there's a kind of restlessness in nature. And that's really what the Schrodinger equation is telling us. The amplitude changes with time. There are a few special cases where you have stationary states, but generally, in terms of any picture with which you describe the physical system, its constituencies change with time according to the forces of your theory. That is to say, that list of rules encapsulated in the vertex diagrams of the theory. Every single part, and you ask, well, what is this? What's another way of looking at it? So the other way of looking at it is every single particle is constantly trying to unwind a whole new world out of itself, because it can continue to emit particles. And these particles know there are other particles around, and they could try to form bound states, and they could have a ball. And at the same time, however, to ravel it back in. Always through the simple steps that change the number of particles by either 1 or 2 in the standard. In other theories, it could be more, and then, well, there. So here's an example of 2 particles coming together. Either we can absorb a particle, so the momentum changes, the photon's absorbed by the electron, or the electron emits, and it keeps going on and on. So you have vertices like this, which have pair creation. And this, of course, the pair is related, same mass, opposite charge, same spin. And you can also have radiation here. So pair creation, radiation, these are the kinds of things that our rules tell us are going on all the time. But sadly, for an isolated electron, okay, if it's just all by itself, kind of out there in a Van Allen belt or something, I don't know. All of these states have energy greater than the electron's energy by some amount, say some delta E. And these are our residual states that everybody knows the concept, and they live for a time of roughly T is equal to H or H bar divided by delta E. In other words, the amount by which the new state has a different energy than the original state. And after this time, these virtual states are wound back in. So we might create pairs, but the pair has to annihilate. And here radiation is absorbed. And then the lonely electron has some friends for a while, but then becomes a lonely electron. Maybe stick them anyway, you know. Okay, you could say this T equals H over delta E is the patience. You know, it creates a big family and says, oh no, I need to watch TV. Okay, so no matter how hard it tries, each particle in isolation returns always to itself, only to start over again. But, and here's where what we do is it's all about. Starting with 2 particles in this state, together they have enough, they can at least have enough energy to produce new states by spending short amounts of time in a series of virtual states. So for example, here's a scattering process. In the initial state, 2, say, electrons come in, they exchange a photon, and the photon carries momentum from one to the other. I mean, it can do it in either direction. And now we can have a final state in which the momentum of these particles is a linear combination of the momentum of the initial particle. So scattering becomes possible once you have more than one particle. And the higher their energy, the more states they can bring about. This is how things happen. So for example, X-rays are made by adding another virtual state. So we have here an electron coming into a target, a charged target, exchange of photon. We have a particle here, which is energetic enough to return more or less to the target momentum, but with the emission of another photon. And this is a photon in an X-ray machine, for example. So then we say, okay, these are pictures. And of course, whose diagrams are these? Again, I know that people know the, you know, but Feynman, thank you. I mean, not that, you know, maybe he hears it somewhere. Okay, so for each process given by a picture, there are rules to calculate a wave height or amplitude. So these are the amplitudes that we're changing through the Schrodinger equation. But very, very complicated amplitudes involving particles moving with great relative velocities. And the amplitude is just a number. So this new amplitude to go from, say, in this case, a scattering initial state to a scattering final state, it's given. Now, the Feynman rules are very complicated, especially the part associated with spin. But at the bottom, they're also very simple as to what they're saying. In this case, we have this 2 vertices from QED, and therefore we have a factor of E squared. E, the number or coupling associated with each vertex. And the amplitude is proportional, roughly speaking, to the length of time, this delta TV, the time which this virtual state exists, where delta TV, as we said before, is like H over the difference of energies, the energy of the virtual state minus the initial state energy. And the rest is all the stuff associated with spin, factors of the particle energy. So it's this delta TV. The smaller that is, and that would correspond to states having, violating the conservation of energy by a larger amount, the smaller the contribution to the factors of particle energy, however, can be positive, and so cross sections can increase with energy. But nevertheless, it's really this factor here that makes things go. And you may notice this, there was from quantum mechanics, you learned something called time-ordered perturbation theory, something perturbation. And that's this time that a virtual state exists is precisely this energy deficit. The difference, the energy that the initial state lacks to produce the virtual state, which is then has to be an intermediate state to the eventual final state. Now, of course, the probability for any process to happen is proportional to the square of the amplitude, just as on the very second slide, the density of photons in a wave is proportional to the square. So, for example, the amplitude that corresponds to the creation of a muon anti-muon pair, an electron-positron pair, and a head-on collision is given by the square of this. And this, when you compute it, is just e to the 4th over 8 pi when the muon is in the same direction as the electron, and e to the 4th over 16 pi when the muon is produced at right angles to the electron. I mean, this is just the kind of prediction that you get out of these scattering amplitudes. Simple, right? So there's this factor of 2. But it gets more complicated quickly with more virtual states. Because E is small, however, this prediction is pretty accurate, even this one here, these two predictions. And these played a very, very important role in the discovery of quarks and gluons, not the original electron scattering experiments, but their confirmation in the annihilation, the electron-positron annihilation experiments at the same facility at SLAC, just a few years later. And it was the ratio of E plus E minus to hadrons over E plus E minus to muons, a ratio that, as many other ratios are, is called R. So it's one of the favorite letters for ratios, as you might expect. And R was like how big R was in different theories, and R was explained by colored quarks. So we had, in that case, we just look back at that list of interactions we had, and for the second interaction here, in terms of a photon, a photon going to mu plus mu minus, it could also go to u bar or d bar with different charges. So that would change the E to some 2/3 squared in the cross section times E, or 1/3 squared. And those were the predictions that worked. And interestingly, and hopefully we'll come back to this, is that the amazing thing is that for that electron-positron annihilation to hadrons, once you get to reasonably high energy, above the mass of the charm core, these predictions are just as true for quarks as they are for muons. And they're extremely accurate. And especially then if you integrate and you get the total cross-section, you really can't tell the difference between the lowest order and the data, unless you really, really do precision at the 1% level. It's actually a nice way of measuring alpha S. So these pictures of, and this is actually brings us back to the observation here. Where is all this having to do with bound states? Okay, so to jump ahead to where you are, we know that quarks produced in a lowest order process like this can never appear in the final state. They have to hadronize. You go to higher energies, you get lots of hadrons in the final state. All this is happening on timescales which are much longer than the timescales where we can use this perturbative expansion, say photon goes to QQ bar. Nevertheless, in the inclusive cross-section, the total cross-section to hadrons, it is dominated by this lowest order alone. So it's that kind of mystery, which, well, maybe I hope we'll get to as we go. Okay, so this is quantum field theory, and you only have to put up with this for another 10 minutes or so today, so it's not so bad. So there's no, and this is, now we get into that other part. Remember that, okay, what makes quantum field theory complicated? It's that you have to renormalize, okay? What's that all about? So that, instead of going to the long times where bound states can form, we ask, well, what about very short times? What happens then? And say the problem is at very short times, the same things can happen, no matter how short the time. So there's no limit to how short a time virtual states might live, and no limit to the energy they might have in these rules. And we go back, I want to emphasize, it's this thing here. The time which these amplitudes are proportional to is the time that the virtual state lives, given by this 1 over the energy deficit. But the problem is we have to add over all the virtual states that can occur. Now, if you think about it, virtual states that can occur, there are a huge number of virtual states that can occur because this photon here in a virtual state can carry any amount of momentum. But momentum is parameterized by a 3-dimensional sphere, of all the directions that particle could be going in. But this virtual state energy deficit is only 1 power of the energy. So you can see there's the potential for problems there. And those problems have to do with counting the number of states at very, very high energies. They differ from theory to theory, and they differ in the number of dimensions that you have. But it also gives you an idea as to why something like this mysterious dimensional regularization that the theorists have certainly heard about, it works because it changes the counting of the number of virtual states. And it enables these little linear energy deficits to give you finite answers by changing the way you count the number of virtual states. So that's just, it's a side remark, but one I can't resist. Okay. So here we are. Now, what we might do is we might say, okay, I'd like to measure how big is the coupling of an electron to a photon. So I imagine, okay, well, what I'll do is I'll have an electron somewhere inside a little sphere, and it'll move into some sphere of radius r, or diameter 2r, according to the black arrows there, and I'll see if it emits a photon, which then I could do another interaction to see, even if it were off shell, whether was another photon there. And we say, well, at lowest order, well, we know what this is. It's G. This is just the amplitude. It's just G, because that's the vertex. Okay? But also, because our Schrodinger equation is true at all scales, now you could say, maybe it's not true at all scales. Nobody has any evidence of that, but it's an interesting possibility. Well, here's what could happen. The electron comes along, emits a photon. The photon splits into a pair. The pair moves along, then there's radiation. And we saw that before. Now there's a pair, and the original electron after some zigzagging, and the photon that we want to see. And eventually the pair, which probably is violating the conservation of energy by more than the radiation, if we choose the kinematics right. So it reforms because its time has run out. T is greater than that particular delta T. Okay, that's good. And then we are back. Okay. So if all this, so this is indistinguishable from the other, as if I'm not able to resolve timescales for this creation of a pair while the radiation was occurring. This is just like if you straighten these out, this is the original lowest order, but now with something else going on next door that doesn't show up in the final state. So this makes life more complicated, but we can actually calculate how all these diagrams depend on R. And this is kind of amazing. It's a little bit of an exercise in, Fourier transform from momenta to R, but you can do it. And this is called, and the fact that then if you insist upon defining your coupling by an electron coming into some radius, emitting a photon and coming out as an electron and therefore in a different direction, how this depends upon this radius R. And you say, okay, I'm going to choose my R and not look inside and just see, what I get for this effective coupling. This coupling in this sense is called a running coupling, and it runs with this variable R. It's usually quoted not with R, but rather the de Broglie wavelength, not wavelength, momentum associated with R, so H bar over R. R plays the role of lambda, basically. So, and you can do this. And this is okay, that's renormalization. Right? You phrase things in such a way that you ask the question of what, as a function of some regulator, in this case, a regulator given in coordinate space, your effective coupling or your resulting 3-point coupling is. So this is for QED, this is very calculable, and you can see it in experiment when you go to very, very high energies. It's a small effect because E is at a situation where R is essentially sent to infinity, E is completely finite and quite small, 1/137 for E squared over 4pi. Yeah, here we go. So what do we see? Okay. States are collections of particles that don't change in time, right? And if we look at what an electron really is, it's an electron by itself plus all this other stuff. Okay, so again, here's our rule from the Schrodinger equation. And here's a typical picture that we saw before by following these ideas. And so we can have pair creation, pair annihilation here and there, radiation, all these are virtual states, but the electron always returns the electron if it's not a scattering experiment. So individual electrons are really collections of these states and more, more than just this, but it's still just an electron and in quantum field theory with some friends. And which friends are there just depends on the mood it's in, okay? And to some extent, what we're going to do is we're going to look at the protons and see its friends by trying to do measurements while it's in those excited states. Okay, so that's, okay, so the next thing that's going to happen is what makes QCD different? To some extent, that the last slide here is to say, the electron for quantum electrodynamics, for most applications and experiments that we can do, this is a perfectly good picture of an electron. An electron is just an electron. If you start to do precision measurements, you begin to see the effects of these extra virtual states that it's in for short periods of time as the electron moves in isolation. But in QCD, of course, this is not the whole story. And that's where we'll begin tomorrow in the second part of this series of leisurely walks through quantum field theory and through QCD. We'll see why QCD is different. We know why it's different because G sub S is much bigger than E. And also it has this amazing property of asymptotic freedom. Okay, so it's that, yeah, no surprise there. But we'll try to approach it from this point of view and see what insights that we can get. So, okay, thank you.
Questions?
There's no, why that?
It takes one day to get them started. We will start asking you questions this evening, so you have to retaliate now. Don't wait. You have to start discussing this evening already. Anyway, what's the questions for you? Go ahead.
Yes, if you come back to the slide with the running, is this, I mean, is that an approximation or is this like,
It can be made. This can be, you can do exactly this by summing over all of the, now normally what we do. So what made Feynman and Schwinger famous? Okay. And Schwinger particularly, because he this one. And that is, instead of doing this rather complicated pair creation here, they just had a radiation of a photon and then the absorption of a photon in the process of the coupling of an electron to, in this case, a zero momentum photon here. So this is how you calculate the correction to the magnetic moment of the electron. Okay, in this particular case, you just have an electron. Well, you have very, I mean, this photon here is just part of a strong magnetic field. And so then you can literally calculate this as a function of R. Alternately, you can show, and this is the way it's done in practice, that a cutoff of R, saying I'm only interested in processes that occur with this diameter of 2R, I can have a momentum cutoff on the momentum carried by this photon, which will be then given a number like mu, something like that. And these two calculations are in one-to-one correspondence. But the momentum cutoff is a little bit less, it's not as easy to see what we're really doing. Okay, so in that sense, though, these are, it's precisely this, it's this change with R that we're seeing. We're not actually, so maybe I should try to make this clearer than I, in fact I did. We're not actually calculating this because we run into trouble when these 2 points come together. And this then lives for a very, very short amount of time. Here we get certain benefit to our calculation from the energy denominators, and there are 2 of them here. I mean, 2 of them, there are more of them if you have this, but if you just have a photon, there are 2 energy denominators because they're 2 virtual states. But there's still so many sum over intermediate states that you that the integral will diverge. But what people saw was that for the running coupling, what you're doing is you're not asking what happens when I shrink this thing to 0. You're not actually calculating this thing from first principles. Rather, you say, suppose at a certain R, I had a charge. And I said it was some value, E naught or something like that. And then I'll say, now let me change R by a little bit. It's the derivative with respect to R that we can actually calculate. And that's what we calculate when we renormalize in QCD or in any quantum field theory. So maybe, yeah, well, go ahead.
does that rate change with how big R is? The rate of,
Well, it will, the whole thing has let's see, I mean, what we do is we assume a value at a given R. And then we just assume it, okay? And then we change R by a little bit. And we can say whatever value we had, that will change by an amount that we can calculate as a higher order. And the amount that we calculate would be higher order in R. In fact, because it will be due to this particular process. And so it's that taking the, isolating the R dependence that makes this meaningful. But you always have to put some information in. So you have to say, okay, well, I chose an R, a likely R of some sort, and then I'll assign a value to the coupling at that R. And there you have to make an appeal to experiment and say, okay, in this experiment, I have a scale that acts like R, and I do a calculation and I say, to get that result, I must have had that coupling at that scale. Then I can calculate how that coupling will change. But this is really kind of neat, because then if you have two different experiments where I say the value here should be one thing, the scale here should be one thing, scales there should be the other, I have to be able to start with this, the first one to get to the second one, or this, but equally start with the second to get to the first. And this is the so-called renormalization group equation, or the running of the coupling in a QCD. When you see all these beautiful agreements between different experiments, they're exactly doing that. You could say you could make the measurement anywhere and run the coupling, and you will get to the value that you would find if you made the experiment at a different scale. Well, anyway.
Thank you.
So, but it's in the sense all in there, but I should have really in this picture, it should be like a little, arrow back and forth, because it's the change in R that we can calculate, not the value, we can't do the sum over all of these contributions from these virtual states, because there are just too many of them. And that's what like string theory is all about. It's to give you a theory in which, as you go to these very, very energetic states, you either have fewer of them or they're reorganized differently so that the interval actually converges. Anything else? Otherwise, I should say otherwise, I should encourage.
Yeah, ask a trivial question. So you said, well, we have particles in height of rules, and so we can trace what happens with time. So what is a particle? It's an electron, 13.8 billion years old, and de Broglie says, well, it's a wave. Yeah, we know it's a wave, but it's a peculiar wave that won't stay occupying very tiny amount of space without spreading all over the universe. So what do you call a particle? We all know what a particle is, but how would you?
Well, I think it's
What keeps it for 13.8 billion years occupying this very tiny amount of space?
It's just the rules tell you that if you look close enough, you'll find these particles in any wave. And in some sense, Einstein wasn't thinking of, the square of the average is the electromagnetic wave, but the electromagnetic wave is, in that sense, the de Broglie wave. And so de Broglie's great observation was that this relationship between wavelength and energy didn't just correspond to electromagnetism, but rather also to matter itself. And that's because Einstein was talking about the electromagnetic wave. It says you have the wave, it's all over the place. You can't say what's going to happen. But its energy, if you look you have some reason to believe the energy arrives at one point, for example, by coupling to an electron. And people thought, well, whatever it is, the electron is for all intents and purposes a point, which it remains today after another 110 years or so, 120. Nevertheless, when you look for where the energy of the wave is, it's in terms of these particles. And it's not, it's the particles are that thing. That waves express their energy content. that waves use to do that. But these are truly profound questions. Yes.
I have a follow-up question to that. So in that sense, right, when you think of particles as kind of along with their friends, so what determines universality in that sense? Is it that they speak to the same friends?
It's every particle, electron
Right,
over here, electron over there, have the same friends.
yes.
And in fact, those friends are all the particles of the Standard Model. There's no particle of the Standard Model that can't communicate with the electron through some series of virtual states. And of course, normally you'd have to create pairs and so forth. Still, it'll be present. And it's part of what makes the electron evolve in time. And the thing we call the electron is all of that. But when we probe it at relatively low energies, then we'll see the electron as basically being itself, or occasionally plus another photon. And when we probe it, that photon may be freed, and that's how, for example, we produce X-rays.
Muons, like electrons and muons, for example,
Well, the muons will,
right? Because they're supposed to be universal, right? In the
oh, yes. Oh, you say the universality, for
Yes.
example, in terms of their interactions. So what will differ is simply the energy of the state that the muons evolve into in any given frame compared to the energies of states that the electrons evolve into. So all of the friends, in that sense, will be the same, but they will live for different amounts of time simply because the muon, which is preserved because of the same universality, the muon number is conserved. But the muon that results in these virtual states does influence the energy of the virtual states. And so its virtual states are typically shorter than those of the electron, which I think is partly why, for example, in our detectors, the muons pass through so effectively because their friends never get to kind of look around the neighborhood. Oh, wait a second, there's there's a calorimeter here. Let's do it. The electron's friends are living a long time, especially, but the muon's friends are kind of stuck close in. And they say, I get the feeling they're having a ball over there, but, we got to get back home.
Let's thank George once again. Lunchtime, we have 1 hour and a half. We have to come back at 1:45. Let's start at 1:45. Sounds good?
1:30.
1:30, we can do it. 1:30, 1 hour, 20 minutes.
Yeah, I will be walking over the, Dunkin' Donuts is open, but East Side Dining is open. I'm gonna be walking over there, so if people want to follow me. Again, because, for dinner, you can go across the
Should we
railroad
close the
track.
doors such that they can leave?
Oh, we're gonna lock the room, so you can leave things here. We will lock the room and, yeah.
Belongings here, we will.